Welcome, everyone. In today's lecture, we are going to be talking about truth tables. Truth tables. Let's jump into the material. Truth tables are still a part of our section on propositional logic, which is also known as sentence logic, sentential logic, and it is a sort of deductive logic. Remember, we drew a distinction between inductive arguments and deductive arguments. If you've got a good deductive argument, you essentially have a proof. You've established that some conclusion follows with absolute certainty. It follows necessarily from the premises given that they are true. Remember, with an inductive argument, the type of support that you garnish is probabilistic, doesn't prove the conclusion. It establishes it to some degree of high probability. So what are some of the things we can do with these powerful truth tables? Well, one of the most important things that we are eventually going to be able to do is use truth tables to show whether or not an argument is valid or invalid. Now, at the beginning of this course, I told you that to some degree, we innately or culturally, we have a logical ability. We have a sense of reason and rationality. And with that alone, we can often determine if the conclusion of a deductive argument really does follow from its premises, whether or not it's valid. So sometimes you can tell just by looking at it, just by reading through it. Sometimes you just instantly can tell. Sometimes if you reflect on it for a little bit, you can figure it out. But when arguments get complicated enough and they have enough nuance, sometimes it's difficult or epistemologically too tall an order, almost impossible to know whether or not it's a valid argument. And so what logicians did is they devised a methodology. They devised a step-by-step procedure by which they could accurately and quickly figure out whether or not the argument's valid or not. So that's one of the things we're going to be able to do with these truth tables. We can also use them to determine the truth or falsity of individual statements based on the truth values of the components or parts of those statements. And there are a few other things we'll be able to do as well that we'll eventually get to. Okay, let's start with some definitions. So what exactly is a truth table? Well, remember, we're doing propositional logic. So at the heart of our artificial system, our artificial language, are statements or propositions. And there's an assumption that statements of this sort must either be true or false. So the vagueness that we examined in other parts of this course, we are setting that aside, and we are only looking at things, in this case, propositions or statements, which are black or white. It's all or nothing. It's true or it's not true. And if it's not true, then it's false. So if we start with that assumption that every proposition or statement, so again, loosely we say of sentences that they are true or false. And on some systems, that's perfectly fine to say. But one of the assumptions that we made in this course is that sentences express statements or propositions. So propositions or statements are the meanings of sentences. It's what they express. And it's not so much the sentence that is true or false. It's its meaning. It's the proposition expressed by the sentence that's true or false. I hope that makes sense. So given that assumption, we can define the truth conditions of all of our connectives, which we've also called operators. So let's do some examples. You know I love examples. We'll start off with negations, which arguably are the most simple kind of complex or compound molecular statements. We know that capital letters A through Z, those are symbols that represent simple or atomic statements. So A could stand for Andrew is tall, or W could stand for today is Wednesday, or W could stand for water is H2O. Here we have P, and P is a metavariable. It's a variable for a variable. So P is a variable for any well-formed formula, any woof in our language. And we looked at what defines a well-formed statement, which we call formula as a synonym in propositional logic. So what are some examples of well-formed formulas? Well, watch the end of last lecture. So capital A is a well-formed formula. Capital A and B is a well-formed formula. If C, then D is a well-formed formula, and it can get very, very complicated. All of those can be abbreviated with this metavariable. So this is a lowercase p, and it stands for, again, any statement that's valid, which is a woof, any well-formed formula in our system of propositional logic. And by definition, that statement's either true or false. It's either true or false. Hence, the negation of that proposition is going to have the opposite truth value. So if P is true, then not P is going to be false. So that should be pretty clear, I hope. And of course, if P is false, then the negation of P, not P, tilde P, is going to be true. So negations, as we would expect, flip the truth value of the statement. Again, if P is true, not P is false. If P is false, then not P is true. So this is the very simple truth table. You can see why we call it a truth table, because it delineates all of the possibilities truth-wise for our statement here, and in this case, it's the negation. Let's do another one. Let's do conjunctions next. So remember, the symbol that we use to represent a conjunction is the dot, and I said in other systems they have the ampersand or maybe the caret. So this represents not merely the conjunction of capital P and capital Q. It represents any conjunction. So remember, P could be A, or could be A and B, or could be A or B. So this could represent the conjunction of A and B in parentheses, or A then B. Any conjunction, complicated or not. Well, P and Q is a composite of P, right, the left conjunct, and Q, the right conjunct. So here's what's called the characteristic truth table for conjunctions. Suppose that P and Q are both true. Well, then the conjunction thereof is also true. Suppose that P is true and Q is false, or vice versa, then the conjunction thereof will be false. And if both parts are false, the conjunction certainly is false. Let's use an English example. Suppose we're looking at the conjunction represented in this statement. Ryan bought cake and ice cream. And we might abbreviate this or symbolize this as C and I. And so in that case, P would be a placeholder for C, which stands for Ryan brought cake, and I would be a placeholder for, or Q would be a placeholder for I, which is, you see how there's the English, there is the object language, which is sentence or propositional logic, and that would be C, and we can annotate this. Let's do that. So this is English, and then this is what we did last time. We learned to translate English into propositional logic. Right, so this is English. What language is this? Propositional logic. In general, what kind of statement is this? Well, it's a conjunction. And how do we represent conjunctions more generally? Well, instead of using capital letters, we're going to use lowercase letters. So that's what the P and Q here represents. So what language is this? Well, it's a meta language. These are variables for variables. So this is in the meta language of propositional logic. Okay. So really, the way that I often think about this truth table for conjunctions with respect to this example is I imagine the four possibilities or four possible worlds. Philosophers love to talk about possible worlds. So in this first world, both P and Q are true. And that's the world where I do what I say. I brought cake and I brought ice cream. And so if I do both those things, then if you were to say this, I brought cake and ice cream, that's true. But in world 2 or 3, if we think of these, in order 1, 2, 3, 4, in the second and third world, I fail at bringing one of these two things. So in the second world, it's true that I brought cake, but it's false that I brought ice cream. So if you said that I brought both, you would be saying something false. And in the third scenario, I do bring the ice cream, but I don't bring the cake. And so to say that I brought both is wrong. It's false. And of course, this last world represents one where I don't show up with either. I didn't bring cake. I didn't bring ice cream. And so to say that I brought both is certainly not true. Sometimes students, they think of conjunctions as something difficult to make true. And I think that mnemonic device works. I mean, there's something maybe not quite right about that, but I get where people's minds are going when they say something like that. You need the stars and the moon to align for a conjunction to be true. You need every part of it. In this case, we have two parts. We need both parts to be true. So if you have any falsity, falseness or falsehood or falsity, it's like a virus and it just spreads. So if you have it anywhere or everywhere, it's just going to spread to the whole thing. Yeah, so that's the truth table for conjunctions. Suppose we change one word in the sentence. We change the and to an or. And remember, I said it's perfectly fine to think of or in terms of the phrase at least one, or at least one of the following. So if I brought cake or ice cream, I brought at least one of these things, maybe both. And that's because we said by default, or statements or disjunctions are inclusive. inclusive. So if I wanted to say A or B, but not both, I would need to express that by putting parentheses here and then the negation of both. But this is inclusive. I'm saying I brought at least one, maybe both. So this stands in contradistinction to conjunctions, because instead of our falseness spreading like a virus, with disjunctions, it's the reverse. It's truth. If you have any little bit of truth in part or everywhere, that spreads. So with conjunctions, it's falseness that is contagious, but with disjunctions, it's truth. Of course, if it's all true, that's easy, then it's true. But if even you have a little bit of truth in your disjunction, well, as one of the disjuncts, then it spreads to the rest. Okay, let's go through the four worlds. In the first world, I bring cake, I bring ice cream, and so to say I brought at least one, that's true. It's only so I thought you brought just one. Well, no, this isn't just one. This is at least one. We could express just one. That would be Ryan brought cake or ice cream, but not both, or and not both. To disambiguate that, you would have to say that out. We don't have to, but that would do it. It would clear things up. Okay, so world two. This is a world where I bring the cake, but I don't bring the ice cream. Bring the cake, but don't bring the ice cream. So true or false? Did I bring cake or ice cream? At least one of them. Yeah, I brought the cake. So that satisfies this or. And so the wedge is true. And similarly, if I forego the cake, but I bring the ice cream, then this junction is still true. Saying I brought at least one. And these are both true. In this case, because I brought the cake. This case, because I brought the ice cream. The only way a disjunction can be false is when both parts are false. So to make me a liar, or to make this statement false, so I was going to bring at least one of these two things, is if I show up empty-handed, I don't bring the cake, nor do I bring the ice cream, then it's a lie to say that I brought at least one. So that's the truth table for disjunctions. So all we have left is to do the horseshoe, the conditional, and the tribar. So this is where students can get tripped up a little bit, and it's not as intuitive as the tables for negation, conjunction, and disjunction. So let's just jump straight to the example. I think if you start with a clear example when you're learning, I want to say you can never go wrong, or it's harder to go wrong. How about that? Okay. Let's say you took a class and the professor made the following deal with you. The professor said, if you get an A on the final exam, then you will get an A in the class, regardless of your performance earlier in the term. So that's not a bad deal. So let's go through the four possibilities. First scenario, you hold up your end of the bargain, you get an A on the final, and then when you go online to look at your grade, you got an A in the class. So is what I said true? If we think of this as a promise, did I keep my promise? If I did, then what I said is true. I expressed a true statement. Yes. So if both parts of the horseshoe statement are true, then the horseshoe is true. So notice that we can assign truth values to the statement parts, to the simple statement parts of a compound statement, and we can also assign a truth value to the statement as a whole. And if it's compound, then that assignment will go to the main operator, the main connective. In this case, there's only one, this horseshoe. So again, if P and Q are both true, then the horseshoe is too, and that rhymes. All right. World 2. You hold up your end of the bargain. You get an A on that final exam. But then when you go to look at your grade at the end of the term, you do not get an A. It's false that you get an A in the class. So did I keep my promise? No, I lied. I told you that you aced the final, you aced the class. But what I said isn't true because you did ace the final and yet you didn't get an A in the class. So I lied. And it turns out, you can see here, this is the only case, the only way, if you will, to get a false horseshoe, to get a false if-then statement. Only one way. It's just like disjunctions. There's only one way to get a false disjunction, when both parts are false. With a conditional statement, which represents the logical relationship of material implication, it's when the antecedent, the left side, is true and the consequent, the right side, is false. It's the only way. That's the only way to get falsity. So that's one way to remember this, is just focus on the exception and then know that the rest of them are going to be the same, in this case, true. So let's go through the last two scenarios. I'm actually going to skip this third one because perhaps it's the trickiest scenario. So let's go to the last one. This one should make sense too. Last one. I don't give you an A in the class, but you didn't meet the condition. You don't get an A on the final. And so you shouldn't be surprised if you didn't get an A in the class. Did I break my promise? No, you didn't hold up your end of the bargain. And so I don't have to come through on, I don't have to deliver in that case. And that does nothing to invalidate my promise. And so the horseshoe, it keeps its truthness. Hopefully that makes sense. So you don't get an A on the final, you don't get an A in the class. Does that invalidate or make me a liar if I present this as a promise? No, it does not. And so the truth remains. In the third scenario, hopefully this makes sense to you, but what happens? You didn't get an A on the final. You didn't get an A in the final. And yet when you go to look at your grade at the end of the term, an A shows up. So did I break my promise? It's like you didn't hold up your end, and yet I still delivered. Does that mean that I lied? Well, no, because I didn't say the only way to get an A in the class is to ace the final. If I had said that and you got an A even though you didn't ace the final, then I lied. But notice I didn't say this is the only way. What I'm really saying here is here's a way. This is enough. This is a sufficient condition. I'm not saying it's a necessary condition. It's a sufficient condition to get an A in the class. And so perhaps you didn't meet this sufficient condition, but maybe you met other sufficient conditions. So maybe you got an A for participation part of your grade, or you got an A on all the other exams, including the midterm, which is worth a lot. Maybe you aced all the quizzes. And that's the reason you got the A in the class, and not because of meeting this condition. And so my promise is not tarnished by the fact that you didn't meet this condition and still ended up with an A in the class. So we're gonna end up with a true conditional statement here. And so we should be clear here. Students, they see a little bit of falseness and they jump to think, oh, that must mean the whole statement is false. But that only happens with conjunctions. Part of the statement is false, so the whole thing is false. It doesn't necessarily happen with disjunctions, right? Part of the statement is false, other part's true, we still have truth. And here, part of the statement is false, part of it's true. We don't necessarily end up with falseness, only in this one case. And then just be careful here, because people see, look, every part of the conditional statement is false. So students, they mistakenly think that must mean the whole statement is false. And there's something that seems right about that, even though it's not. It seems like, well, if everything about it is false, then the whole thing must be false. But notice, that would be an example of the fallacy of composition. We mistakenly believe that what's true of the parts has to be true of the whole, but that's not the case here. What's true of the parts is that they're false, but the whole is true. And that's just the nature of the conditional, the relation of material implication. All right, so we just have our last connective or operator, which is the tribar, the triple bar, which represents the English if and only if. Let's say that I say, hey, here's a way to get an A in the class as you ace the final. And by the way, it's the only way. So it's a sufficient condition, but it's also a necessary condition. So you'll get an A in the class if you ace the final, but only if you ace the final. That's this if and only if. This logical direction goes both ways. Well, let's go through the 4 scenarios. Well, if you got an A in the class, and I kept my promise here, did you get an A on the final? Yes, definitely. Definitely. So let's go through that again. So in this world, you get an A in the class, you get an A on the final. Did I keep my promise? Sure. Yeah, that was in line with what I said. So that's why we have a T here. Okay, what about world or scenario 2? Well, you get an A in the class, but you didn't get an A on the final. But wait a second, I said this is a way and the only way. So how could that be? That must mean that I lied. And that's why there's an F here. Same thing with the third scenario. This is where you get an A on the final, but you didn't get an A in the class. Wait, but I said that this is a way that if you ace the final, this is a way to get an A in the class. And so I did get an A on the final, and yet I didn't get an A in the class. So this was a lie. So we have a false here. And if you don't hold up your end of the bargain, you don't get an A on the final, and I don't give you an A in the class, then that doesn't invalidate my promise. So you didn't do your part, so I don't do my part. Both things are false. My promise still remains. It still holds. And so the trick that I keep in mind when it comes to biconditionals is I look for sameness and truth value. So there are 2 parts here, if you will, the left and the right side of the biconditional. And by the way, the order doesn't matter, right? So we could take this, you get an A on the final clause, and we could move it to the front and move this, you will get an A in the class clause, and move it to the back, and the meaning wouldn't change. And so symbolically, that would look like Q if tribar P, Q if and only if P. And that is logically equivalent to this. So what we want to look for, like I said, is sameness. So if both parts, the left and the right part here, represented by P and Q, if they're both true, then the statement as a whole is true. Similarly, here they're both false, but we have sameness. And when they are the same, then the truth value of the connective is true. It's only if you think of these as rows, row 1, 2, 3, 4. It's only in rows 2 and 3 when you have a mismatch where one part's true and the other part is false, or vice versa. That's when the tribar ends up being false. So I'll say that again. When both parts are true, the tribar is 2. Similarly, when both parts are false, they're the same, they're both false, the tribar or triple bar is true. But when one part's true and the other part's false, or one part's false and the other part is true, that's when you end up with a false biconditional. So that's it. We went through the truth conditions for all the characteristic truth tables for all 5 operators or connectives. And here we have it all on one slide, right? So the negation of a statement just flips the truth value. For and, you need both parts to be true. Otherwise, you end up with a false statement. For or statements, all you need is at least one part of the statement to be true or both, and you end up with truth. Or in other words, the only way to get a false disjunction is when both parts are false. Otherwise, you end up with the true disjunction. With the if-then statement, the horseshoe, the only way that this can be false is when the antecedent is true and the consequent is false. Otherwise, the statement is true, even when both parts are false. And for the biconditional, like we just said, if you want to end up with truth, you need sameness in truth value. So you need both parts to be true when they be the same, or they need to be same in that they're both false. If you have a mismatch, like a T and an F or an F and a T, you end up with a false triple bar statement. Now that I know that was a lot, but now that we have learned that, we can already do all sorts of powerful things. So we can practice in chapter 6. So we're looking at 6.2. So let's go to, I think that this is an extra, this one shouldn't be here. We're at 6.2, and then this is 6.2.1. Yeah, I don't think we want this here. 6.2, and then we're going to do, yeah, Roman numeral 1, 2, 3, 4. Okay, that's better. We already did this first section, Roman numeral 1, in the previous lecture, where we just identified the main operator, the main connective, so like, for example, in 1, the main connective is the dot, right? So this is the left conjunct, the right conjunct. In 2, it's this horseshoe. Let's see if we can find one with a negation. Like in 3, this wasn't, it's part of your homework, but we didn't talk about it. In 3, this is a big negated statement. This is the main connective here. It's not this dot or tribar because the dot only applies within the brackets and the tribar within these parentheses. And the reason why the author or authors of our textbook put finding the main connective in 6.2 is because it's essential. You have to be able to find the main connective if you're going to do these truth tables properly. So let's go to 6.2.2. And here we're actually going to use a little bit of we learned before of symbolization. And then we are going to figure out if the statement is true or false. You see, so again, we're doing a lot of symbolic stuff, and you might be thinking, this is getting very mathy. This is starting to feel like algebra, like maybe it's good just for me to work out that quantitative ability and that I kind of use that in an everyday sense, but this kind of exercising my mind has at best an indirect and is indirectly beneficial to everyday sense. But here, we're evaluating propositions, we have to do that all the time. So are these statements true or are they false? Well, one way to determine as much is to do it given what I've just taught you about truth tables. So for example, first we have to symbolize this statement. France bombed Pearl Harbor, or Lindbergh crossed the Atlantic. So this is an or statement, and the left side is France bombed Pearl Harbor, so we could represent that with F. The or will represent with the wedge, and Lindbergh crossed the Atlantic would be F or L. So we've symbolized the statement. That's what we learned about in the previous lecture. But now we're going to figure out if this statement is true by looking at this statement and using truth tables. Well, so here we're just going to use our knowledge of history. So France bombed Pearl Harbor. That's false, right? So it was us, if you will, the United States. So this F is false, so that's appropriate. And Lindbergh crossed the Atlantic. So this will be a good test. So a lot of you might not know this off the top of your head, and even I think that's right. I think Lindbergh was the first person to cross the Atlantic in an airplane, without stopping on an island or something to get fuel. But let's say that you didn't know. Could we determine the truth value of the or if we didn't know this? Well, it turns out no, because if this wedge is going to be true, we need at least one part to be true. We know the left side is false, right? This is false. And so if this is also false, then the or is going to be false. But this is true, it's my understanding. And so it's going to make the or also true. And that's because, whoops, I didn't mean to delete that. It's because this L is true. And so this is true too. Okay, so this is part 2. Yeah, F or L, true, because Lindbergh did cross the Atlantic. Think about this, you're the first person. No one has gone that far, or maybe they've gone that far on land, but you're going over the ocean. If you run out of fuel, you might not make it. Okay. Where's my clear all drawings? I don't think you guys can see that, but so be it. All right, let's do another one. Julius Caesar conquered America. Some of these are funny because they're so ridiculous. If Napoleon ruled France. Well, Napoleon ruled France. That's true. Did Julius Caesar conquer America? No, he died even before America was a country. So we have an if in the middle here. So what follows this is the condition, right? This is the condition. And let's say that that's N. That's the condition of the conditional statement. And the consequent is Julius Caesar conquered America. Napoleon ruled France. Sure. But Julius Caesar did not conquer America. That's false. And remember, this is the lethal combination. When the antecedent is true and the consequent is false, the horseshoe is false, right? So that's this scenario here. So a lot of times people they'll symbolize it, they'll get the truth values in, and then when they're trying to figure out what's the value of the connective, they often go back to this chart here. But eventually you'll get good enough at these that you'll just kind of have this memorized. So 6 is N horseshoe J, and it is false. N horseshoe J, and it's false. Okay. Yes, these are kind of fun. You start with like little bits and you kind of fill in all the information. It's kind of like Wheel of Fortune or Hangman or crossword puzzle. So I'm not biased, but yeah, these can be, once you figure it out, it's pretty rewarding when you can do it on your own. Washington was assassinated only if Edison invented the telephone. Okay, we'll say Washington was assassinated. Let's say that's W. Only if Edison invented the telephone. Let's say that that's E. And we have an only if here. And so we're going to capture that with a horseshoe. And we have to be very, very careful. In 6, this is very similar. It says if, this is only if. Are they two different ways of saying the same thing? No, they express the opposite logical relationship. So if you have a if by itself, this is the condition. But if you have only if, you can represent all of this with the horseshoe. And so the condition actually comes before the only if, which is a plain if. The condition comes after. So that certainly can be confusing. But, if you just remember what follows in if by itself is the condition, the antecedent, that can be helpful. Or, you can go back to your notes. In general, if you have P if Q, that's going to reverse the order. You're going to end up with Q horseshoe P. And if you have something only if something else, you got to keep that order as it appears. Okay, now let's do the truth values here. Washington was assassinated. I don't think he was. That's false. And Edison invented the telephone. Edison, we think of him, I don't know, you might think of like light bulbs and, electricity or something. But Alexander Graham Bell, I think that's ringing a bell. I think he's the telephone person. So I think those are both false. And again, you might be tempted to say, oh, if both parts are false, the whole thing is false. But remember for the horseshoe statement, when both parts are false, the whole statement's true. The whole statement's true. It's only this lethal connection when the antecedent's true and the consequent is false. So that was 7. And we have 7. We have W horseshoe E. And we said that it's true. Now, students also get confused. They're like, wait a second, there's an F here, there's an F here, there's a T. Which of these is the truth value of the whole statement? Well, it's the one underneath the main connective or main operator. Well, W and E, they're not even operators. There's only one operator. So this represents the value of the whole statement. This F, it only represents the truth value of W. This F only represents the truth value of this E. I hope that makes sense. Okay. Cool. Let's do Roman numeral 3 here. A and X. And we are assuming that, so this is just given in the instructions, that A, B, and C are true and X, Y, and Z are false. Okay. We can do this. So we said A is true. You know what? Let's we just need a little bit more. Let me do this. Let me do this. No, mouse should do it. There we go. Just need a little bit more room here. Okay. So we said A, B, and C are true. So the earlier letters of the alphabet true. The latter ones toward the end are false. So we have an and statement. A is true, X is false. But with an and statement, falseness spreads like a virus. And so the whole thing is going to be false. So number 1, exercise 3 is false. Just like we said, false. With 2 here, B is true. Again, if you're wondering, how do I know that? It's just in the instructions. It says A, B, and C are true, and X, Y, and Z are false. All right, so there's a couple ways to do this. Here's the most doing all the steps way. So Y, ignore this negation for a second. This Y is false. So Y is false, and then not Y. Underneath this negation, we can say that it is true. Why? Because if Y is false, then the negation of Y has to be true, right? So if Y, in this case, let lowercase p be this variable for Y, and if that's false, oh, sorry. No, we're doing here. Y is false. That's what was here. then the negation thereof, the value is flipped. Then not y has to be true. So that's one way to do it. The other is just to kind of skip a step, and you can see, well, y is false, so then not y, you can kind of maybe put the f underneath the whole thing. That would be acceptable too. Not y is false. So we have an and statement. The left side's true. The left side is true, but the right side is false. So that means the whole statement is false. False. Falsity. There's all these ways to make it a noun. Falseness, falsehood. Falsehood's probably the most natural. Falsehood spreads like a virus. That still sounds a little bit funny. So 2 is false. Oh, I see what I did. I went too fast. Geez, got to be careful here. I just said that not y was true. You see, even someone like me who knows this stuff like the back of my hand, you can see if you go too fast or you don't double check your work or you make one small mistake, it can lead you astray. So let that be actually comforting to you that, hey, you're going to make mistakes and you still will make mistakes, and that's okay. But so it's good. So the lesson is, double check your work, definitely, and don't worry about messing up. Sorry, we said y is false, and so the negation thereof, of course, would be true. So some of you might have been kind of yelling at me through the screen or been like very confused. So we want a big T here, and so both parts are true, which of course is up here. So this is going to be true as well. Yeah, and so that's what we're looking for here. True. So I apologize about that. Okay, now let's do a horseshoe statement. So what's B? Well, remember the earlier letters we're just assuming are true. That's the assumption for this exercise. Like in the next exercise, they could assume the opposite or something totally different. They could assume A, B, and C are all false, or that A is false and B and C are true. So that's just, and you might say, where do we get those values? Those are just made up. It's like we make up examples that, Okay, so this is true. So Z is false. So not Z is going to be true. So we skip that step. Or if we want to do it in all its glory, we could say, well, right under the Z is false. And then the negation thereof is true. So we have a horseshoe statement. Both parts are true. That's world 1. So the whole statement is true. So 5 is true. 5 is true. Now we have a triple bar statement. And we know B is true. We know Y is false. These are the assumptions. Oh, and we have a mismatch, right? These are not the same truth values. And for the triple bar, when you don't have the same truth values, you end up with falsity or falsehood. So 8 is false. Okay. For 10, this is good because we have this negation on the outside and some parentheses. Okay, so A is true by definition. Z is false by definition, which means not Z has to be true. And now we're going to do the dot. The left side's true, but what about the right side? You might say, I can't tell. Look, there's a T and an F. Well, we should focus on this T because it represents the main connective in this right disjunct. So, you could even kind of like cross this out if you want to sort of ignore it. It could be helpful, or erase it. So we have a conjunction. Both parts are true. And so this and is true. But this negation It's negating the main connective inside of the parentheses, which is the and here. So if A and not Z, I'll say that again, if A and not Z is true, then the negation of that true statement must be false. Isn't that cool? That was even more complicated. So 10, you should expect a false here, and we've got it. We've got it. With 11, we're getting more complicated. So B, we know, is true by definition. The negation of a true statement is going to be false. Y is false by definition. Again, if you look at the instructions here, that's where we get that F. A is true by definition. So inside these parentheses here, we have a horseshoe statement. The left side's false, the right side's true. So what goes here? Well, we could look at the chart, but hopefully now you're like, oh, I remember that's true. So one little bit of kind of interesting information is with the horseshoe statement, let's say all we knew is that the left side is false. It doesn't even matter what the right side is. This has to be true. Because if A is false, you have two F's, which for a horseshoe statement yields a true under the main connective. And if A is true, you still end up with a true horseshoe. Similarly, let's say I started by putting in the A as true. And let's say we didn't know what Y was. It doesn't matter. The horseshoe still has to be true. Because the only way to get an F here is when you have T horseshoe F. And if you have a T on the right, there's no way to get T horseshoe F because you would need an F here and we don't have it. And in the earlier case where we knew Y was false, it doesn't matter what A is because if Y is false, there's no way to get T horseshoe F because you would need Y to be T, but it's true, but it's false. So this is false, right? This was just suppose. No, this is just kind of what's the way to get false here. All right. Now, what do we do now? Well, what's the main connective of this whole statement? It's not this negation that only negates the B. You know, it's not this horseshoe that only applies within the parentheses. This is the main connective. This, I'm trying to draw an arrow here. Trackpad drawing. I'm gonna have to up my game and get kind of like one of those tablet pencil things. So what's the value of this wedge? Well, it depends on the left and the right parts. So we have to know where to focus here. The left disjunct of this wedge statement is not B, and this F represents the truth value of this left side. So you can kind of ignore this T. And this T represents the truth value of this right disjunct, this right part of the or statement. So we can ignore these now. And we have a disjunction where the left side's false and the right side's true. And with disjunctions, that means this junction is true. So you can look at this chart here, or you can just remember that with disjunctions, truth spreads like a virus. So the wedge is true. So 11 is true. All right. Hopefully this is sinking in. What's cool is you can pause, you can rewatch, you can watch this on 2x speed. And my voice goes, but I think I go back and forth between I can take long pauses And so when you watch this on 1.5x or 2x, it actually sounds a little chipmunky, but it can come off kind of smooth. But yeah, that can work. But then I get excited. I can talk really, really fast, and then it might sound even more chipmunky. All right. Is this the last one we're going to do? Yeah. For this section, that is. So 15. All right. So Y, false by definition. C, true by definition. B, true by definition. X, false by definition. Not X is going to be true. It's going to flip this truth value. This horseshoe, we can ignore this now. Both parts are true, so the horseshoe is true. Sorry, the horseshoe is 2. Excuse me. This is the negation of that true horseshoe. So this is going to be false. Right? So now I can ignore all of this. Look at this. This is an and statement. The right part is false. And so it doesn't matter what the truth value is, the left part. We know the answer is going to end up being false here. So 15 is going to be false, and it is. But we can still finish this up if you want. So this is a horseshoe. The left side is false. And so you can see it doesn't matter what the right side is. Horseshoe is going to end up true. And so we don't need to look at these anymore. We're looking at this and statement. The left side's true. The right side's false. And of course, that's going to make the and the dot false. Cool. So I think you should be getting it. Hopefully this is sinking in. Let's see. Do we want to do 4 here? Yeah. When possible, determine the truth values of the following symbolized statements. Let A be true and B be true, Y and Z be false. Now, see, in this one, we're practicing with question marks. P and Q have unknown truth values. If you can't determine the truth value, write undetermined. Okay, yeah. This will be good too. So Q and Y, this is a question mark, I believe. Let's make this a little bit bigger. Ooh, that's a little too big. We can practice this one. Y, we said is false. So we have an and statement. We don't know about the left side. The right side's false. So that's going to make the whole statement false. Doesn't matter what Q is. Because falseness, because I could say falsehood. I really want to say falsity or falseness. Falseness spreads like a virus. So 3 in this next section is false. 3 is false. Maybe if I do extra zoom world, we can use this. 5. P is one of those question mark ones. B is true. Oh, this is good. So the horseshoe statement, if the right side's true, the horseshoe has to be true. You look at this horseshoe statement. Where is Q true? In rows 1, right? If you think of this as row 1 and row 3, that's where the right side's true. And we end up with true horseshoe. So it doesn't really matter if it's true or false. So that's what's going on here. That's what's going on here is we have a true consequent, so it doesn't matter what the antecedent is. So 5 is going to be true. What part are we in here? I think we're, yeah, true. Okay. 6. Oh, this is another good one. I mean, it's like I picked them, so it makes sense. That's a good one. So Q, we don't know, but it doesn't matter. So similarly, when you have a false antecedent, oops, I'm looking at the conjunction, sorry, here, when you have a false antecedent, where P is false, it doesn't matter what these are, true, false, you end up with a true horseshoe. So 6 is true. Yeah, 6 is true. Cool. Or, yeah. Sweet. Sweet, sweet, sweet. Okay, let's do a little bit more and then we can call it. So so far we have been doing truth tables for individual statements. I mean, it's had, you might say, well, aren't there 2 statements here? But this is the individual statement. And then to come up with the truth values for it, we need truth values of its parts, right? This is this individual statement. These are its parts. Individual statement, its parts. Individual statement, its parts. Individual statement, its parts. So now what we are going to do is work on truth tables that can get longer. And in terms of rows or lines in the truth table, there's a relationship between the number of rows or the number of lines and how many simple statements or atomic or simple propositions are in the statement or statements plural. And you can see this doubling effect in these first 2 rows. But the doubling goes away once we get to, 1 doubled is 2, 2 doubled is 4. But look at this. This is 3 doubled is an 8, 4 doubled is 16. You might say, well, is it squared? Like 1 squared? Oh, that's not 2. We have some squaring. And so really, with each proposition that you add, the doubling is over here, right? So if you have one simple proposition, like here we have P, then you're going to have 2 lines or rows. If you have, so maybe I should show you this first. If you have 2 simple propositions, call them P and Q, then it's going to double the rows. Instead of 2 rows, you're going to have 4. If you have 3 simple propositions, that's going to double the amount of lines or rows from 4 to 8. From 4 to 8. And if you have 4 simple propositions, call them P, Q, R, and S, that's going to double the rows or lines from 8 to 16. And so what is the reason for this doubling? Well, it's to capture all of the truth combinations. So if you have one statement, call it P, it's either true or false. If you have 2 statements, call them P and Q, well, either they're both true, they're both false, or one's true and one's false, and vice versa. If you have 3 statements, P, Q, and R, then you're going to have 8 combinations. They're all true, they're all false, 2 are true, and 1 is false. And there's another, these 2 are true, and this one is false, and these 2 are true, and this one's false. You can see this is to get all the combinations. So there are exactly 8. And logicians have come up with this pattern for a couple of reasons. One, it ensures that you get all the possible worlds or all the scenarios, all the truth conditions. And 2, by having this standard, then one logician's, remember, a logician is someone who studies logic, like a magician is someone who does magic, a logician is someone who does logic. If we have this standard, then your truth table is going to look like my truth table, because there's different ways to map this out, you could kind of try to do it off your head. Okay, well, there's P, Q, and R. Then, well, P and Q could both be true and R could be false, but maybe P and Q are both false and P and R, are false and Q is true. And then they're both, you could have a different order of these 8, right? You could have these 3 rows first, so this is just a standard. So the tables all look the same. There is a way to express this mathematically. So if you're a very mathematically oriented or minded person, it is an exponential function. So if you take 2 and you raise it to the x power, so we're doing exponents here, and x is the number of statements, then you're going to get you're going to get the number of rows. So here there's 1 simple statement. So that's what you put in for here. So 2 to the first power is 2. Here there are 2 simple statements. So 2 to the second power, 2 squared is 4. Here there are 3, 2 to the third power is 8. Here there are 4, 2 to the fourth power is 16. If there have been 5, 2 to the fifth power is 32. If there have been 6, 2 to the sixth power is 64, and so on and so forth. So now what we're going to do is we're going to use truth tables to classify statements. We can categorize or classify every statement in propositional logic into one of 3 categories. Statement is either a tautology, a self-contradiction, or a contingent statement. A tautology is a statement that can't be false. It's logically true, it's said. It's tautological. It's tautologous. A self-contradiction is a statement that can never be true. It's necessarily false. It's logically false. And then, so most statements don't fall in, well, it's hard to say most, but at least in courses like this, when you do these exercises, or how about this? Most of the propositions that we hear, read, say, and write, they tend to be contingent, meaning that are they true or false? It depends on how things play out. It depends on how the world is. It depends on how the world shows up. It's contingent upon the facts. Every once in a while, you might say something that can't be false. There's a tautology that shows up in Confucianism, I believe, or Zen Buddhism, those koans, Zen koans that you're supposed to reflect on until you achieve enlightenment. So one of them goes like this: wherever you go, there you are. Or it is what it is. Well, by definition, I think, right? All men are men. All flowers are flowers. These things can't be false. They're necessarily true. They are tautologies. They're tautologists. Tautological. It's kind of a mouthful. Or some things that are self-contradictory, right? So something biblical. I am the Alpha and the Omega. I mean, maybe that makes sense, but if you tweak that to so Alpha is the beginning, Omega is the end, in the Greek alphabet. But so if you define the end as not the beginning, I guess we don't have to do that, but if you did, then that would be I am the beginning and I am not the beginning. Well, you've just contradicted yourself. And so at least in propositional logic, when we analyze that statement, the truth table, it's going to end up being false on all lines in all scenarios. If you're saying like, I'm wearing blue jeans, well, that's contingent. That depends on, so the days you are wearing blue jeans, that's true, but the days you're not, that's false. So that depends on how the world is. So let's do some truth tables and practice this. So we want 6, 3, 1. Use truth tables to determine whether these are so this says tautologist, self-contradictory, contingent. I like to say, are they tautologies, self-contradictions, or contingent statements? Oh yeah, I mean, this one I can just tell. This is saying if n, then if n, n. This is a long-handed way of saying if A, then A. Well, of course, so fill in A. If it's Tuesday, then it's Tuesday. So if you meet that condition, then of course it's going to be right. So it's just going to be a tautology. But we can prove it with the truth table. Well, let's see, how do I want to do this? So what are the symbol statements that make up this statement? Well, all I see is n. And that's one simple statement, and it's true or false. And then here's the statement. And in row 1, we can number these if we like. You don't have to. Sometimes I like to. In row 1, n is true. So if it's true here, it has to be true everywhere it appears in this row or line. So let's work inside these parentheses. This statement is and then n. Both parts are true. Well, we have a horseshoe statement where both parts are true. And so the horseshoe is 2. Now we can ignore these. And we have another horseshoe statement with both parts true. And so that means the horseshoe is going to be true again. And now we can ignore these. What about when n is false? Okay, well, if it's false here, it has to be false everywhere else it appears in the line. Let me explain that again. Maybe that's kind of fast. So this is kind of like a grid, right? A grid. Yeah. We're in row 2, and we're looking at n. N in row 2 is false. So n everywhere in row 2 has to be false. So n is false here, n is going to be false here, and it's going to be false here. So I want to find out the value here, but to do that, I need to find the value of the consequent. To do that, I have to look at this horseshoe statement. Both parts are false. You might think, oh, that means that this horseshoe is false. But no, remember, remember that when the left side of the horseshoe is false, the whole thing is true. Or just when both parts are false. That's what we actually have. Both parts are false. The horseshoe is false. Sorry. You got to be careful. When both parts are false, the horseshoe is true. It's true, true, true. Okay, so I can ignore this. And then I have a horseshoe statement. Then I have a horseshoe statement where the left side is false and the right side is true. That's, you look back at the table, the the horseshoe will be true here. So this is the main connective. And so you can either kind of cross out what's left. You can erase it if you want. You can even just keep everything and just kind of, I like to oval it sometimes. And so what we notice is, irrespective of whether n is true or false, the statement as a whole stands true, which means that it can't be false, which means that it is a tautology. It is a necessarily true statement. Underneath the main connective of the statement is all t's in that column. So this statement, if n, then n, is just a long way of saying something that can't be false. In fact, you could just keep adding the condition of n over and over again, and it doesn't change the meaning. It just weakens it. So crossing out this n horseshoe, what's left has the same meaning of the original statement. And you might say, well, can you boil this down? Can you fuse it just into plain n? No, you cannot. This says n if n. N if n is different than saying n. Think about it. What if n is it's Wednesday? So this would say, if it's Wednesday, then it's Wednesday. Well, yeah, sure. But just fusing that into saying it's Wednesday, it's a much stronger statement. If you're saying it's Wednesday, you're saying it's Wednesday. But this is saying it's Wednesday on the condition that it's Wednesday, if it's Wednesday, which is a weaker statement. One of them has to be true. The other one depends on what day of the week it is. Okay, let's do another one to practice. So here we have a conjunction of if S then R and S and not R. S and not R. So I can tell by looking at this that this is going to be a self-contradictory statement, because if S is true and R is false, but it's also supposed to be the case that if you meet the condition of S, then R follows, then R is going to follow. Like we have S, and this says if S, then R. So we have R, but we also have not R, and that's going to be the contradiction. So this whole statement can never be true. So underneath its main connective, we are going to have all falses. Let's see, this it just says what the answer. Oh yeah, number one is a tautology. So how do we do 3 here? Well, I like to start by drawing a horizontal line. That's pretty crappy. I know what I can do. I think this will work. Ah, look at that. That's a beaut. Okay, so what letters do you see? I see S's and R's. And so the convention is to put them in alphabetical order. So R is going to go first. So you mentally erase all the symbols and you just find the letters. What letters do you see? And then put them in alphabetical order. Q, R, S, right? So R comes before S. Okay, so we have 2 letters. So that's going to tell you how many rows you need. We have how many letters? We have 2, so we're going to need 4 rows. Or you can look at how many simple propositions. Those are the letters. We have 2, so we need 4 rows. Okay, so we could number them if you want, so you don't have to. So we need 4 rows. Sometimes I like to draw a horizontal line here. And then we need to put this whole statement over here. And we need to put in the truth pattern here, which is right here. So we have 4 rows. This is the pattern that you will always put in here. This is the pattern. row 1, they're both true. In row 2, R is true, S is false. In row 3, you get vice versa. In row 4, they're both false. And now we're going to fill in the rest of the table based on this information. What's the main connective in here? Well, it can't be this horseshoe. That only applies within these parentheses. It can't be this and. That only applies within these parentheses. It has to be this conjunction. That's the main connective. And so we really care about the truth values, the 4 truth values under it in this column. If these are all T's, then this is a tautology. But I already said I suspect that it's a self-contradiction. So we should expect all F's here. If it were contingent, we would have at least one T and at least one F. So now we fill in the values here based on what we see here. So in row 1, R is true. So in row 1, all the R's have to be true. So this R is true. This R is true, which means not R is false. S is true in row 1. So this S is true. This S is true. This is a conjunction. All right, so we can kind of ignore this. This is a conjunction of a true statement and a false statement, which is going to be a false statement if you remember the truth table. Right, so now we can ignore this and we can ignore this. This is S, then R. Both parts are true, so the horseshoe is also true. This is an and statement. You can kind of ignore this, ignore this. An and statement where the left side's true and the right side is false. And that's going to make the and statement false. So we do have an F here as we suspect. Remember, for and, falseness spreads like a virus. In row 2, R is true. And it doesn't even matter what S is, right? We have a horseshoe statement. If the right side's true, the horseshoe has to be true. So I'm not even gonna do this part. Doesn't matter. In row 2, S is false. And I know the truth value of this and. It has to be false. Because falseness spreads in an and statement. So it doesn't matter what's over here. And I don't need to look at this. I don't need to look at this. This is an and statement, and the right side is false, and so this is going to be false. In row 3, R is false. Do I need to look at the antecedent? Yes, because it depends. If the antecedent's false, then the horseshoe is going to be true, but the antecedent here is true, and we have that lethal combination. We have a true antecedent and a false consequent, and when you have a horseshoe statement, that's going to make it false. And I can kind of ignore this for now. S in row 3 is true. Do I need to keep going? Yes, because I don't know what this and is going to be based on the true left side. R is false, and so not R is going to be true. So I can ignore this. But really, I didn't even need to do this part because we have an and statement. The left side's false, so the and has to be false because falseness, falsity, falsehood spreads in an and statement. And when everything is false, S is false, which means that the horseshoe in this statement is going to end up being true. I don't really care about this. The S here is false, which is going to spread to this and make this false. And it doesn't matter what's here. It doesn't matter what's here. It doesn't even matter what's here. We have an and statement. The right side in row 4 is false. That's going to spread to the main connective. And so you can see, no matter how you cut the pie, we end up with a bunch of falses. This statement's necessarily false. It's a self-contradiction. So that is 3. It's self-contradictory. Yeah. All right, let's do one more and then we'll call it a day. Let's do 5 here. Let's draw our horizontal line. And we can type these out so it's a little bit less messy. We have not K, H. Oh, we need some parentheses here. And of course, I forgot we had to start with what letters do you see? I see K's and H's, and we're going to put them in alphabetical order. And do this. We need, we could put a line here if you want. We're going to have 4 rows again. And we need our horseshoe. We need our triple bar. And we are good. Always good to double check. Okay, the pattern. One way to do it is with a 4 row. The leftmost column is 2 T's, 2 F's. And the second columns go up and down, lines or rows go left to right vertically. Left to right horizontally. The second column is going to be T, F, T, F. In other words, the leftmost column always will, first half will be trues, second half will be falses, regardless of the size. And the rightmost column in your atomic or simple statements section of the table will start with T and then alternate all the way down. All right, now we need to fill in this. What's the main connective here? Well, it's not this horseshoe or this negation. It is this triple bar. Now, a lot of times it's in the middle of the statement, but not always. If you put brackets around all these and negate it, it could be out in front. So we care about the truth values underneath this triple bar. And in row 1, all the H's are true. And it doesn't matter what's going on here. If I have a horseshoe statement, the right side's true, this horseshoe is going to be true. This H being true is going to make this wedge true regardless of K. So I don't care about this anymore. I have the negation of this wedge. This wedge is true. The negation of it then is going to be false. So the right side of this biconditional is false, and the left side is true. We have a mismatch. You remember with the biconditional, sorry for this messiness here, but the biconditional, when you have a mismatch of T's and F's, the TFs is row 2, the biconditional ends up being false. Remember, if I'm ever going too fast for you, you can always pause. You can rewatch. That's the beauty of this. Okay, so we know this cannot be a tautology because it would need all T's, and we have at least one F. So it's either self-contradiction or a contingent statement. Let's go to row 2. In row 2, H is true again, which means that this horseshoe is going to be true. And so if this statement on the right is true, we can stop because we'll have our answer because the triple bar will be true. It has to be a contingent statement. So H is true. which is going to make, we just did this. So the wedge has to be true because it spreads like a virus for disjunctions. And it's the negation thereof. And so the negation of a false statement, negation of a true statement is going to be a false statement. And we end up with the same thing. It's going to be false again. All right, let's try row 3. In row 3, H is false. So we do care about what's going on over here. K is true, so not K is false. We have a horseshoe statement. Both parts are false. You might think that that makes it false, but it actually makes it true. So we've yet again another true statement. And in row 3, H is false. Does falseness spread like a virus? Not in disjunctions. It does in conjunctions. K is true. So this truth will win out in this disjunction. And we have the negation of that T. So we have an F here. And yet again, we end up with a false statement. So this is looking like a self-contradiction, but I think we're going to see. Well, actually, I didn't. See, this is getting so complicated. So what do you think just by looking at this? This says, if not K, then H. This says not both. Sorry, this says neither H nor K. And it's the if and only if relationship between these two things. So another way to think about that is if you start with this conditional statement, do you end up with this one? And if you start with not this one, you end up with this statement. If you start with this neither nor statement, do you end up with this? Let's find out. Well, in row 4, both parts are false. So this not K is going to end up being true because it's the negation of a false statement. This H is false. And so this horseshoe, this is the lethal combination, true antecedent, false consequent. You end up with the false statement here. All right, we got something different. And here, both parts are false, which is going to make the wedge false. Make both parts false. We have the negation thereof, which means that this is going to be true. And we have a mismatch again. So this statement is self-contradictory. Well, because if it's neither H nor K, we're saying H is false and K is false. Well, if H is false, then that's going to make we can see it's getting very complicated. And that's why we do the truth table. Because when it's that complicated, sometimes you can't tell just by looking at this. But this statement is necessarily false. This is not it's false that either H or K. So you're really saying H is false and K is false. That's what this is saying. And if K is false, then we've satisfied this condition, which means that we should satisfy this condition. But so we should end up with H, right? Okay, if K is false, we have this as a condition here, which should lead us to H. So we can get H out of this. But we're saying H is true, but we're also saying that it's false. So that shows that if you start this way, you're going to end up with a contradiction. but this is a triple bar, so we can start over here and we'll end up here. So if we start here, this is saying that one way to interpret this conditional is you're saying that the following conjunction can never hold. It can never be not K and not H, right? We can never have a true antecedent, which is not K, and a false consequent, which would be not H. And when you do De Morgan's on this, which we learned about in a different lecture, you're going to end up with K or H. And we're going to learn a rule called association that lets us reverse the order here to H or K. H or K. That's another way of expressing this conditional. Either H or K. It's another way of saying this. But if that's your starting point, how could you end up with the negation of that? So that's my point. So I've been doing this a long time, and so I can, I have to talk through it, but I can see and I can explain that this has to be a self-contradiction because if we just said if you start with this, you end up with the negation of this. And if you start with this, you end up with a contradiction. And so this statement is a lie. It's not true. And it's a self-contradiction. I thought we were going to do one that's a contingent statement. But I guess I didn't assign one. Two is contingent. So I guess we could just really quickly, just so you could see it. So this, let's do it. Let's do it kind of sneakily. It's just two. So you could see, we saw a tautology and two self-contradictions. So we're going to cheat. We're going to write it underneath here. And so the simple statement is G. We're going to have G either true or false. If G is true, then this G is true. All these G's are true. But it really doesn't even matter what's going on over here, because if you have a true consequent, the horseshoe has to be true. And in row 2, G is false. So it has to be false here. We don't even care what's going on here, because if you have a false antecedent, the horseshoe has to be true. And so we can ignore these. And so now in row 2, we have a horseshoe in which the left side's true and the right side is false. That means that the horseshoe is false. So the main connective here is this horseshoe, right? It's not this one. That only applies within the parentheses. It's this one. And you can see under this oval, under this column, we have at least one T and at least one F. And so 2 is going to be a contingent statement. So slowly but surely, that's the way to do these, and double check. So we're going to do other things in the future, the last little bit of this class, this course, where you, it won't be as tedious. You won't have to double check as much, and you won't have as much as the domino effect that like one little mistake can snowball and ruin everything. That's the downside of these ones. But the upside is that hopefully, as you start to do these, you realize that every individual step is actually quite, I hesitate to say easy, but it's actually, I'd say it's quite doable, I will say, especially with enough practice. It can be a little bit tedious, but if you kind of just give yourself some time when you're in a good mood, you can kind of deal with doing a little bit of tedious, but each little part is doable. These can be kind of fun. All right. Okay, so we did that. So we'll wrap things up there. So all we have left to do is compare statements and then do truth tables for validity. So that will be in the next video on truth tables. All right, everyone. That was a lot of fun. That's all I have for you for now, and I will see you next time.